Well, hello finally, guys. I am very sorry it's taken this long to get everything put together on my part, but good news is I've got two things I want you to do, and that's it. I'm not going to give you guys a final exam. I've got this chapter to go over, then I have one more thing that I will do. I will get it out to you by tomorrow, and I will make sure you get a list of all the things I need back from you. But right now, I just got two new things to get you, and we'll go from there. I hope you guys are doing okay. I know it's probably very stressful on your part too, and I'm sorry that I haven't been a little bit better in that regard, but we're okay now. We're here, so let's get this done. I don't know how long this video is going to be. I'm going to try to streamline it because if it's a video, you can always rewatch it, right? I'm going to go through the principles of our chapter 11, which is technically our last chapter in the book. We actually really did a good job getting stuff done. I mean, I don't know why we were so ahead of the game, but I'm glad that we were. So after this, I have one more topic to show you, and that's it. But let's get through this one today. I will, accompanying this video is also a assessment. I decided not to give you any other worksheets to go over or anything like that. Figure if you can go right from here to the assessment, we're good. And if you have any trouble, then you can let me know. We'll take care of it from there. All right, let's start with this one. We're all about triangles right now. We're going to talk about similarities and congruences of triangles. Okay, so we're going to start, first of all, with how do you know if you have a triangle or not? It's called the triangle inequality theorem, actually, not the triangle sum theorem. I kind of made a mistake there. Let me fix that. It's called the triangle inequality theorem. Basically, what it means is, can these three things make a triangle? So can you have a side of 3 inches, 9 inches, and 8 inches and have a triangle? Well, there's a couple ways to do it, but I find that this is the easiest one. You take any of the two numbers like 3 and 9, you add them up. You get 12. You subtract them. And we're just going to do the absolute values here. Okay, we'll just say the absolute values. The third side has to be between 6 and 12. And guess what? 8 is between 6 and 12, so that's a yes. Okay, that's it. How about this one? 37, 13, and 21. Take any two sides you want, it doesn't matter. We'll take 37 and 13, add them up. That's 50. Subtract them. Whoops, how did that happen? And what do we get? 24. So the third side must be between 50 and 24. And guess what? It is not. It's too small. So the answer is a no. The other way people think about it is you take the two smallest sides. Like in this case, you would take the smallest sides. You would take 3 and 8. 3 plus 8 is 11, which means if you laid those out and stretched them out flat, you would have 11. Does 9 fit inside of 11? It does. Here, our two smallest sides are 13 and 21. You add those together, you get 20. Oh, wow, you get 34. So 34 is as wide as they stretch out. Will 37 fit into a 34? No. So that's another way to think about it. We kind of already did it, but we'll kind of go over a little bit more. So if I give you two sides, can you tell me what the range of the third one is? Well, we just do what we did before. We add them up. That's 26. We subtract them. And that's 8. That means that that third side must be between 8 and 26. Now, can it equal 8 or equal 26? What do you think? If you lay 9 and 17 and 9 down, you get 26, and 26 is flat. 26 will fit on top of 26, but then it's not a triangle. It's just a straight line. So you got to have it, it's got to be less than 26. I mean, even 25.99 would work, but it's got to be less than 26, and it's got to be more than 8. If you laid those two pieces, 9 and 17, next to each other, there'd be a gap of 8. So you need something a little bit more than 8 to fill that gap in. Okay? That's how it works. So we take this one, we'll add them up. 30 plus 11, 44. 30 minus 11, 19. The third side must be between 19 and 44. Okay? That's how the triangle inequality theorem works. Remember what the triangle sum theorem was? That was just saying that three triangles add up to be 180. Or three angles of a triangle have to be 180. That's the triangle sum theorem. Sorry about that. All right. Congruence statements. So what I'm going to ask you to do is write a congruence statement. Congruence statement means these triangles are congruent to each other. Congruent means they're equal. So we match up all of these parts. Like if you look at triangle ABC and this triangle DEF, well, you have to match up parts specifically. So angle A would equal what in the other triangle? Well, that's the right angle, so it's got to equal angle D. So D must go first in our congruent statement. All right. B, and you can see the way it's marked here. It's marked with two separate lines, two little squiggles there, I guess you call it. Same with E. That's one way to mark a triangle, so I'm going to show you another way as well. So B and E have to go together. So B is the second letter, so E has to be the second letter. And that leaves C and F. Now, if this congruence statement is written correctly, everything in the congruence statement about the triangles is correct. Angle A is equal to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Side DE is congruent to side AB. DE, AB. It should always work out that way when you do a congruence statement. Everything has to match up perfectly. Over here, U. Well, U had the two little slashes, two little arcs there. Goes with X. And it's kind of important to write a triangle. It's a triangle X. V is the second letter. V has the one arc, so it matches up with Y. And how nice. They put it in alphabetical order, X, Y, Z. That's a congruence statement. And that's important to know because we're going to be talking about congruences the rest of, well, for a while. Not ever, not forever, but for a while. Okay, so that's a congruence statement. Oops, let me erase that. Let me put that back. I lost a little bit. Okay. Now, we don't have to do all of these. I just want to show you what's going on. It says identify the corresponding sides. So if you look at X and K, or indicate, indicate means we're going to mark them up. I'm going to show you different ways to mark. I'm going to mark them up differently for 1 and 2. But I know X and K should be equal. So we saw one way that they do it. They just put one little slash. Y and L should be equal. Put 2. And Z and J should be equal. 1, 2, 3. It's supposed to be arcs, sorry. More like that. Whoops. That didn't work nice. Let's try that again. 1, 2, 3. Okay. Now the sides. XY, we'll put a little 1 mark there, should be equal to KL. Alright. XZ should be congruent to first and third letter, KJ, which leaves this side and this side to be congruent. That's one way of marking. The sides are always marked the same with little slash marks. Sometimes the angles are different, and I'll show you the different one in this case. All right, P and T are the same. So I've also seen it, and you'll see the book sometimes do this. P and T are the same. Let me make this one better. Got a new toy here that I'm starting to just get good at. Put a little slash mark in the arc. P and T are the same. Q and S are the same. So we do a little arc, and I put 2 marks in it. That's S, 2 marks. And then R and R, same angle because, well, not the same angle, but it's coming from the same point, are equal 1, 2, 3. 1, 2, 3. That's how you would mark those. Okay? Alrighty. Oh, I don't know what happened there. That's okay. And for the sides, PQ is equal to or congruent to TS. And these two are the same. And these two are the same. The slashes do not have to indicate necessarily the smallest to largest side. It's just an indicator. Like these were the smallest sides here. Okay. These necessarily were not the smallest sides. We don't really know. I think 2, the side with 2 slashes is definitely bigger than the side with 3 slashes, but it doesn't matter. It's not an indicator of how big they are. It's just that they're congruent to each other. All right, moving on. Now, how do we tell if 2 triangles are the same? Now, we would normally do a project. I love this project where I give you guys criteria. You build triangles, we compare them. One of the things that we know, if I tell you to construct a triangle that has a 3 and a 4 and a 5-inch side, and all of you do it, and it doesn't matter how you do it, how you flip it, how you put it together, when you turn it in, they're all exactly the same. We're not going to go through all the proofs of it. We're just going to go through how they work and how you can use them and what we call them. That's all I need you to know how to do. So the first one, side, 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 SSS. If you can show that all 3 sides of a triangle are congruent to each other, then the angles are also congruent to each other. All right? So it says use the SSS congruence property. So we know that AB, we know that for this one, there we go. We know that AB is congruent to DC. We also know that BC is congruent to AD or DA. Now, AC, both triangles share it. So AC has got to be congruent to itself. That's called an identity property. So if I want you to show, then you showed side, side, side. You showed all 3 of these sides are equal to all 3 of these sides. That's how you use side, side, side. What is the similarity statement? Triangle A, B, C is congruent to triangle. What matches up with A? C. What matches up with B? D. And what matches up with C on A? So triangle, let me draw that better, triangle. Triangle ABC is congruent to triangle CDA by the side, side, side postulate. Or property, sorry. Okay. What about this one? I don't have to write it all out, but can you show that EFG is congruent to, E would be congruent to J, F would be congruent to I, and G would be congruent to H? So you might be saying, well, I got a right angle in there. You've probably heard of a place called angle, side, angle, or I'm sorry, side, angle, side. But think about it. If it's a right triangle, does that mean if these 2 sides are the same, that's the hypotenuse, that by Pythagorean theorem, these have to be the same also? So you can show it that way and call it side, side, side. Now specifically, we're asking for side, side, side. Normally I wouldn't use side, side, side for that example, but it's okay. It works. The next one, side, angle, side. So if you have side, angle, side, that means you have 2 sides and an included angle. What that included angle means that if you start with a side, okay, and you have 2 sides that you're using, the angle must be between them. It must be the angle that connects both of those sides. This is side, angle, side. Side, angle, side. And the thing is, if you do another triangle that has a side, angle, side, they have to be the same. Okay? Now, if you look at this one right here, notice these 2 sides. The angle D is not known. They say the angle E is that size. Okay, then we don't have a correct property, side, angle, side, but this is, no, It's got a bad name, but we'll talk about that later. But do you notice how this angle is not the angle that connects those two sides? So these are not congruent. At least we don't think that they are congruent. We cannot show that they're congruent. And I think you can see that they're not congruent. So they are not congruent. All right, what about these two triangles? What about triangle RTS? What's that congruent to? R, you kind of flip it over here. You see how R and U would be the same? T is still going to be T. And S is going to be V. Now, why do we know that side angle side works here? Well, we're given two sides. Do we know the angle between the two sides? Well, if you remember, if two angles make that little X shape, we called them vertical angles. And vertical angles have to be congruent to each other. So this angle T and that angle T have to be equal. So we have side, angle, side. Side, angle, side. Those two triangles are congruent. And there's more. What about angle, side, angle? So angle, side, angle is another one. You have two angles and the side between them. So here's already an example one that's not true. You've got two angles, but you need the side between them. I need to know about this one. And guess what? I'm not told about this one. I'm told about this one. So I cannot guarantee that these are congruent. And in fact, if you look at them, they don't look congruent, do they? So, not congruent. Now look at this triangle. We have these two triangles that are connected. We have F, B, and S. So let's say triangle BFS would be congruent to triangle B, and T would be the same. They have the same angle. F would have to be the same as M. And then, again, these two angles are the same, aren't they? Because they're vertical. So angle S is equal to itself. So do you see how we have our angle, side, angle? We have the two angles and the side is right between them. So we've got two angles and the side that connects them. All right, two angles and the side that connects them. So that's angle, side, angle. Now from angle, side, angle, there's another one we could use. There's really the similar thing. Like if I know that, and this picture is exactly the same as the other picture, and that's for a reason. So if I know that this angle and this angle are equal, well, if I know those are the same, you know the triangle sum theorem. The triangles have to add up to 180. So whatever this is, 30, 40, 50, doesn't matter. If I take these, add them up, subtract from 180, isn't F going to be the same as M just because of the triangle sum theorem? So if that's true, I have these two angles and a side. The side does not have to be between them. It just has, as long as you have two angles and a side, you can say the same thing. So this could also be shown as true by angle, angle, side. Two angles and any side you want. Now, it's one of my favorites. I love doing this when I'm in math class, because especially with the grade school, the high school kids, really. You say a word like that, they're like, whoa. Okay. Angle, side, side is not a congruence property. It does not work. Okay. It's kind of fun that it doesn't work. It does not work. And here's an example. So in blue, these two are the same. This is congruent to this. This is congruent to this. So I have two sides, but not the angle between them. Oh, by the way, real fast, in books, in high school books and stuff, they call it side-side angle because they don't want to say, that word. Okay, we'll cross that out. So you have these two known sides, and you have this known angle. So do you see in this triangle how these are all true? This angle and this angle are the same. This side and this side are the same. This side and this side are the same length. But you see how this one right here, I can swivel it and hit that triangle in two different areas. The green side, I didn't say had to be a certain length. So the green side can be any length you want it to be. So you have these two triangles that fit that criteria. But as you can tell, these two triangles, so it'll be this one and this one, are definitely not the same. So no angle side side, unless you want to call somebody an angle side side because it's fun to do. Another one that doesn't work for congruence is angle angle angle. Your angles can all be the same, but it doesn't mean your sides are the same. Just like a stretch or a shrink. Okay. So summary. What are the the four properties that you have? Whoops, wrong one. Let's come back there. You've got side, side, side. You've got side, angle, side. You've got angle, side, angle. And you have angle, angle, side. These four work. Now there's a couple special ones with a right triangle. These all work with right triangles though, but you ever hear of hypotenuse leg? Things like that. It's really just another word for this. So these are good, and these are bad. Side, side, angle, and angle, angle, angle. They do not work. They're not bad, they just don't work. They do not prove that a triangle is congruent. Okay, so you can't use them. All right. That's it for the symbols for now. Let's look at some mappings. Congruence mapping means how can I take a shape and move it, but it maintains the same size. Okay. Our first one's called a translation. It just simply you move it from one place to another. Okay. So this A, see how it's going to go 1, 2, 1, 2, 3. It's going to go 2 up and 3 over. That means every point is going to follow that mapping. It's going to go 2 up, 3 over. 2 up, 3 over. And you can kind of see how the shape is. You don't have to do it for every point. If you get the pattern down, you go 2 up, 3 over. E goes 2 up, 3 over. Now, shape should maintain the exact dimensions. It's just that it's moving. F, up 2, over 3. Right. G, up 2, over 3. And then H, up 2, over 3. And then I is the same way. So this shape here, like you get yours, is this shape here translated. Everything is just moved this many points that direction. Now I'm not going to label all the points, I just want to show you. We call it now J prime, I prime, don't have it here, but H prime, G prime. Okay, that means it's a new point. Now we can also translate on a grid. If I want to go 1 unit down and 4 to the right, so I kick every point. We'll start with C, go 1 down, 1, 2, 3, 4. This is our new C. A, go 1 down, 2, 3, 4 to the right. B goes 1 down, 1, 2, 3, 4 to the right. So this is C prime, B prime, A prime. And we have our new points. A prime is now 1, 1. B is 3, 1. C is 1, 3. Okay. Now, that's called a translation. Translations just tell you what to move. There's another way to write a translation that I want to show you. Okay. We're going to take our points and move them. Now remember, x is left and right. X is left and right. X goes first. So we go 4 units right. And right is positive. So we're adding 4 to the x. That means we're moving it 4 to the right. We're moving the y down. Remember, y is an up and down motion. So we're moving y down 1. And that is how we do a translation on a coordinate grid. Okay, so this means 4 units right and 1 unit down. Right. Reflect. How do I reflect this image over here? Now, if you have a piece of paper, it's pretty easy. Like a tracing paper, you can trace it, trace that line, and flip it over and tell. But basically the idea is the distance from here to here has to be the same on the other side because it's a mirror. That's what a reflection is. So our new S goes right here. Now you might say it's not always easy to see because this R isn't diagonal 1, so diagonal 1, this should be our new R. But notice another thing about it too. 1 over 1 down 1. So I kind of do the same thing. Over 1 down 1. Over 2 down 2. Over 2 down 2. This worked for V as well. 1, 2, down 1. 1, 2, over 1. So you see, it's got to stay on the same diagonal. So you see how it's 2 dots away from the line. So it's 2 dots away from the line. What about T? Just 1 dot away from the line. Now my suggestion, because sometimes these points they start like running into each other, is I right away I will do that. Now V and T don't connect, see, so don't connect to these two. I probably shouldn't have drawn V. I draw U. See how U would be 2 dots off the diagonal? So U would be here. Now U connects to T, and T connects back to S. So that is how we do a reflection. Whoops, I think I got those backwards, didn't I? This is our new T. This is our new U. Wow, come on. Why, oh why, why? All right. That's how we do a reflection. Now, reflections over maps of far coordinates are a little bit easier. So, x equals 3. You remember what the line x equals 3 is? I'll draw a dotted line for it. X equals 3 would be right there. So, a reflection across the horizontal vertical line is pretty straightforward because all you got to do is if the C is 2 units away from the reflection mirror, the reflection point, then its reflection is 2 units away. Okay. So, notice how F is 1, 2, 3, 4, 5 units away. So its reflection would have to be 5 the other way. 1, 2, 3, 4, 5. Okay. D, 1, 2, 3, 1, 2, 3. And these are all the new points. They get a little prime on them. And E is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That's our new E. Right, so if you look at those, this should be a reflection across this dotted line. Boom, boom, boom. Okay. Oh, and the coordinate points, sorry. They're not as important in this problem, but we'll write them down since they're asked for it. The new D is 0, 1. The new E is negative 2, 1. And the new F is negative 2, 3. Oops. Okay. that's a reflection on a grid. Now we're going to do a rotation. Now rotations are a little trickier to see, which I did. I've actually created a little tool here. I have retraced that figure DEFG, and I put a dotted line to the to where we're rotating around. Okay, so I'm going to take this and I'm just going to rotate it 90 degrees clockwise. Okay, so that's what the shape looks like, 90-degree clockwise rotation. But the question is, where does it go? Well, it should go right there. Make sure that that line is right on O. Now, what does that look like? So I'm going to show you. This one's not the easiest to see, but I'm going to show you how to do this and then do it on a coordinate grid, which is a little bit easier. F, see how you went up 1 and over 2 to get to F? Well, you kind of reverse the process. Up 1 and then to the right 2. Well, now you kind of do it a little bit in reverse. You go up 2 to the left 1. Now, this one, to me at least, is a little trickier to see. I have a hard time sometimes visualizing that. Okay. But once you get the one point, F, well, how do I go slanted? Slanted, I get the G point. And because the G and D will be a lot easier in this case, because look at the G, it's 1, 2, 3 away. And that's what we're spinning it around. So it should be 1, 2, 3 up. The D is 1, 2, 3, 4 away. So its rotation is 1, 2, 3, 4 up. And then E would be this one. The easiest thing, honestly, to do, and do what they say right here, is take a piece of paper, trace it, and then just turn it. Turn it 90 degrees. And you'll see where it should go. So you would trace this, but also trace the dot, because that's where you'd turn it over. Now, coordinate-wise, it's a little bit easier to do, and I want to show you something. Now, I do have the points down here, and I know sometimes, I don't like the points. They're going to help out. Okay, I'm going to do the points of our original graph, 1, 1. Okay, F is 5, 2. G is 4, 4. And H is 2, 5. Now, there's actually a rule about how to do something 90 degrees counterclockwise. Now remember, 90 degrees counterclockwise means we're turning it this way. Okay. Another way to say 90 degrees counterclockwise would be to say 270 clockwise. Means the same thing. So we're either going to turn it 90 this way or we're going to turn it 270 this way. Either way, we're going to end up in the same spot. Remember, 90 degrees is one turn. 270 would be 3 turns of 90 degrees. Remember, 90 is all we're going to do for here. We're only going to do it 90, 180, and 270. If we did 360, we get right back to the beginning again. Now, it is on here. I'm going to go forward a few pages where I have these rotations the formula is kind of spelled out. Now, we were flipping that 90 degrees counterclockwise, which would be the same as 270 clockwise. So we're actually going to use this. And notice this thing says xy becomes negative yx. So let me write that down. xy is going to become negative yx. And let's see if this thing works. Here's what it means to do all that. It means you take the point and you see the x and the y value. We're going to switch their positions. The x number now becomes the second number. Now the y number becomes opposite of what it was. It was positive 1, now it becomes negative 1 and becomes the first number. Now 1, 1 is not, I guess, a great example because you don't know that it's flipped. But for 5, 2, 5 is the x number. It now becomes the second number. The 2 is the second number, which now becomes the first number, but it becomes opposite. Now, if it was a negative, then it becomes positive. This doesn't mean make it negative. This means change the sign. All right, 4, 4. Same idea. It doesn't really matter. 4, 4 is going to be 4, 4. 4 becomes the second number. This 4 becomes the first number, it becomes opposite. And 2, 5. 2 becomes the second number. 5 becomes negative and becomes the first number. Now, when I ask you to do this, these are nothing I need you to memorize. I'm going to send you this document, so you'll have these formulas when I ask you to do it. So let's see if we get the right shape. So negative 1, 1, negative 2, 5, negative 4, 4, and negative 5, 2. So we end up with this. Whoops, not the greatest drawing. Still working on trying to, I just made it worse. Try one more time. Connect those. Connect those. Connect those. Not really well. Connect those. Good enough. We'll leave it like that. So you see how this has rotated 3 times. 1, 2, 3. Or 90 degrees counterclockwise. See how it's gone over that way. That's how we do a rotation. Okay? Now, how do you do a 180 rotation? These are actually one of the easiest things to do. If you do a 180 rotation, all you do, and I'll go back to there, okay, you just take the x's and y's and make them opposite of what they were. That's it. Okay, so what's A? A is 3, 2. Make them opposite. Negative 3, negative 2. B was 2, negative 3. Becomes negative 2, 3. Oh, let me write the rule. I forgot to write the rule for this, so we don't forget. Okay, don't know why we changed. XY is going to become negative x, negative y. Their signs just get changed. C is 3, negative 1. We switch the signs, we get negative 3, 1. D is 4, negative 3. Negative 4, 3. Let's see what we got. So negative 3, negative 2. That's our new A. Negative 2, 3 is our new B. Negative 3, 1 is our new C. And negative 4, 3. Now what I'll do is, I'm gonna not cheat, I'm just going to use my tools a little bit better here. Let's still do the blue, right? Let me just connect these with a straight line, and still not perfect, but so you see the 180 rotation, it flipped that way. And it doesn't matter if you do it left or right, because 180 is 180 either way you do it. Alright, so that is how you do a 180 rotation. And I've left one more, the clockwise rotation of 90 degrees. Our clockwise rotation will be this, where xy is going to become y, negative x. Okay, let's write that down. Xy is going to become y, negative x. So 90 clockwise means it should be up here somewhere. So if we get it up there, we know we did okay. All right, S is negative 2, negative 1. All right, here's how the rule works. The x number now becomes the second number, and it also becomes negative, or it changes sign. So negative 2 is going to be the second number, but now it's going to become positive 2. It changes sign. Negative 1 is your second number, now becomes the first number, just stays the same. T is negative 5, negative 4. So the process, negative 5 is the x number. It becomes the second number, but changes sign. So now it becomes positive 5. And the 4 becomes the first number, or the negative 4 becomes the first number. And u is -1, -5. So we do it. -1 becomes the second number, becomes a +1 because of the rule, and the -5 becomes the first number. So let's see if we end up something up here. -1, 2, -4, 5, -5, 1. And does that look correct? Oops. Okay. Now if you take a piece of tracing paper, you'll see that that is true. It doesn't always look true, but that is true. That's a rotation. Remember, it's not a reflection, it's a rotation. So that's why it doesn't look perfect. Notice how this kind of pointing there towards the 2. This one's pointing towards that 2, so I know it's right. All right, so for your summary, those are all of the rules. Now, we didn't actually talk about reflection rules, but there are reflection rules that can be used. And I'm going to list them there for you to look at. When you reflect across the line y equals x, remember that line y equals x is a diagonal line. And y equals -x is the diagonal line that way. So if I graph something and I say, whoa, that is not good. Try that again. So if I graph something and I say reflected across the line y equals x, well, that's the reflection point. So the point's here. Its reflection will now be down here. Right. Now, I didn't go over really examples like that, but I think you'll be okay. But let me know if you're having any trouble. And the translation is another way to write it like this, and I showed you that. A is the left and right movement. B is the up and down movement. All right. We are almost done. We got a few more slides to go. I was going to stop and make a second video, but I think let's just go through it. Let's just go. Let's just keep on going. Because now we have and I kind of made a mistake again. I see this is not a similarity mapping. I'm sorry, a congruence mapping, because we're not keeping it the same. We're going to make this a similarity. And a scale factor. An example would be if I'm taking ABC and I want it to become smaller or larger, I don't change its shape. It just follows the same scale. This would be our new A, our new B, our new C. If this was halfway down, this shape would be half the size of this. And you could also make it bigger, project it out this way and make it larger. Remember, it maintains the same shape. It just is a smaller and smaller figure. Okay? I can make it as small as I want, as big as I want. That's up to you. That's called a scale factor. Scale factor would be if this is half the distance to that, this scale factor would be a half. It's half as big. Kind of an easy thing to see on here. If I want to make a scale factor of 2, what I'm going to ask you to do is to make it 2 times as big. So P right now is -4, -2. Well, if I'm going to make it twice as big, guess what I'm going to do? It's going to double it. So -8, 1, 2, 3, -4. Now, back here, this was the dilation point where it's going to. We don't have a dilation point. We assume it's the center. Everything's going to go in or out from the center. All right, Q. Q is 2. Nope, it's 1, -2. Well, if I want to double it, it's going to be 2, -4. That's our new Q. That's our new point P. R is 4, 1. So if I make it a scale factor of 2, I'm doubling it. 8, 2. 8, 2 is our new R. And S is -1, 1. Double that one, get -2, 2. -2, -2 is our new S. Now I'm going to use my straight line to make sure I make these nice and straight. When I connect these, this figure should be, all the sides should be parallel to each other. And what I mean by that is, well, that one's not good. Let me try that again. See how PS and the new P, new S, P prime S prime are parallel to PS. Q prime R prime is parallel to QR. And this figure is twice as big. And we can make it 3 times as big and 4 times as big, whatever fits. We can always make it half as big and put it inside. So that's a similarity mapping with a dilation. We call it dilation the same because like your previous dilate and stuff like that. That's a dilation. So here I'm going to make a scale factor of 0.5, which basically means I'm going to cut the size in half. Now the center is here still. So it's all going to come down to that point. So x is what, 6, 4? I said 6 and I wrote 4. So a scale factor of a half means it becomes 3, 2. Y is, what is that, 16, 14? Oh, that was nice, wasn't it? Half of that would be 8, 7. And Z would be 6, 14. Half of that would be 3, 7. So 3, 2, 8, 7, and 3, 7. We'll make that a triangle again. I guess we'll do it in black this time. So notice how the new x prime, y prime, z prime is half as big as this one. And if you followed from the center, this point, see how that hits z, those two z's hit each other? Guess what? The two x's hit each other, the two y's hit each other, because it's all shrinking to the center. It's all going towards the origin. Okay, z, y, x. So I'll just leave it like that because that looks pretty cool right there. That's a dilation. Now how does that help with similarity? Similarity means if two triangles are similar, it means their shapes are the same. Now it's kind of a vague definition, but similarity means that the angles are the same. It's basically what they mean. The angles are the same. Are the sides similar? So we're being told that triangle ABC is similar to triangle DEF. That's just given to us. So can I find the lengths of these other two sides? Well, take a look at it. If these are similar, look at DF and AC. How do they compare with each other? What's the scale factor to get from DEF to ABC? Well, the scale factor would be 3, because 21 divided by 7 is 3. That's our scale factor, which means that these all have a relationship of 3. If DE is 5, that means AB is 3 times 5, or 15. And if BC is 27, then the smaller one, which technically has a scale factor of 1/3 then, would be 27 divided by 3, which would be 9. Now, when the scale factors are whole numbers, they're pretty easy to do. If they're not whole numbers, there's another way to do it, and I'll show you right now. I'll show you on this one. You could say this: 21 over 7 is the same as, say I didn't know what this one was, x over 5. Then you just do a little cross multiplying. 7 times x equals 21 times 5. Solve for x by dividing by 7, and you get x equals 15. So, 2 ways to do it. It's nice when the scale factor is a whole number. It makes things a whole lot easier. So, are these two triangles similar? And if they are, why? So what are you given? You're given that angle A and angle G are both right angles. So we got those. Those are the same. We also know that angle H in both of these are the same because they're vertical. So instead of doing that, let's do the angle H and angle H are the same. Now, because you know, if you have a triangle and these two triangles have angles that are the same, what do we know about this third angle? Whatever that is, if you subtract it from 180, it's going to be a certain value. And guess what? These are going to be the same values. So as long as you can prove that two angles are the same, just two, you know what they call the postulate? They call it angle. That's all you need. If you show two angles are the same in a triangle, they all have to be similar. So the similarity statement would be this. So let's say AKH. Call that a triangle AKH. Similar is just one squiggle. What does A equal? A equals G. K equals E, and H equals H. So this similarity statement means that these triangles have a proportion. So it's possible that this triangle is half the size of this triangle. We don't know what the proportion is. We don't know the scale factor. We just know it has one because of angle. Right? These two triangles, it says that angle N and angle M are the same. Well, what do you also know about these two triangles? They share something. They share angle R. They both have angle R. So doesn't RSN have these two angles? And doesn't RTM have these two angles? And if we can show two angles are the same, then we know the triangles are similar. So in this case, triangle, we'll do the small one. RSN is similar to R, goes with itself, S and T match up, N and M match up. Here's your similarity statement because of angle. All right, we are almost done. Got 2 more slides after this. Thank you for being patient. All right, which 2 of the following 3 of these are similar? So if you look at them, just kind of get some ideas here. So the smallest side on all of them. Let's look at the smallest sides. 8. Okay, there we go. 8, 5, and 6. All right, let's look at the biggest ones and see what we can do. 20, 10, 15. So here's what I'm going to show you right now. We're going to take the small side. Okay, we're going to make a proportion or a ratio out of it. 8 over 20. It should equal, there we go, small to large, small to large, small to large. Well, one of these certainly doesn't fit. 5 over 10 is 1/2. These are not 1/2. So perhaps you could see that those are not the same. Now, I wanted to. I could make a decimal out of them. In fact, maybe I should do that. What is 8 divided by 20? It is 0.4. 5 divided by 10 is 0.5. 6 divided by 15 is 0.4. So guess what? That triangle is definitely not similar to the other 2. Let's just take and compare these 2 triangles, agreeing that that's not a possibility of an answer. So I know that 8 over 16, see if I do that one to the middle, small divided by middle. So let me do small divided by middle. Is this true? And I think you can see that yes, 8 over 6 and 6 over 12 are both 1/2. It is true. These 2 triangles, 1 and 3, are similar to each other. All right, this is kind of tiny, but we're going to get this one done a little bit. Okay. This is about your similarity with perimeter and area. So the scale factor from A to B. So if you look at that, how do you get from A to B? 12 to 3. So we did it before as a whole number. Okay, so 12, 3 is a scale factor. Now if I reduce that, isn't it 4 to 1? Isn't this one 4 times bigger than that? 3 times 4 is 12, 4 times 4 is 16, 5 times 4 is 20. Now what are the perimeters of A and B? The perimeter of A would equal, add these up. So we get 20 plus 16 plus 12. So that's 20, 30, 40, 48. And the perimeter of B, add these up, we get 5 plus 4 plus 3. So we get 5, 9, and we get 12. So what's the ratio? 48 to 12, but guess what? What does that reduce to? 12 goes into 48 4 times. It's 4 to 1. So notice how the perimeters have the same scale as the sides. So that's the point here. The relationship between the scale factor and the ratio of perimeters. Well, it's still 4 to 1. So it's the same as the figure. Okay. Now the areas. So the area of this triangle, area of A. Remember, area is 1/2 base times height. All right, what is the area of A? Well, A is 1/2 base times height. And I've already figured out my calculator. 1/2 12 times 16 is 96. The area of B. B is 4 times 3. Base and height is 4 times 3. 4 times 3 is 12. Half of 12 is 6. Is 96 to 6. Now that's a much bigger ratio than 4 to 1. But is there a relationship between these? So if I divide 96 by 6, I actually get 16. It's 16 to 1. And what do you know about how a number 4 compares to a number 16? It's a square. 4 squared is 16. This means areas, because remember, areas are 2 dimensions. So you're doing it by 4 twice. You're doing it 4 that way and 4 that way. And 4 times 4 is 16. So the areas actually increase by a scale of whatever the scale model is squared. So if it was 4 to 1, it'd be 16 to 1. If it was 8 to 1, it'd be 64 to 1. And here's one last problem to kind of sum that up. So if you got a photograph, okay, and the area of the photograph is 15 square inches. Okay, that's for number 1. And we enlarge it 3 times as big. What's the new area? Well, it's not 15 times 3. Because remember, we made this side 3 bigger. This is more, this is increased by 3. This also increases by 3. Okay? So, if I multiply this side and make this side 3 times bigger, and this side is 3 times bigger, then the whole thing is going to actually be 3 times 3, 9 times bigger. So this is going to be 15 times 9. And 15 times 9, which I should be able to figure out in my head, but I'm a little tired, is 135. So that new photograph is 135 square inches, because it's really 15 times 3 squared. Okay? For this one, if the surface area is 52 square centimeters and the scale factor from the box to a larger similar box is 2, what's the surface area of the large box? So again, we are taking the surface area, and it's just area, and area is 2 dimensions. Area is length, width, that's it, just 2 dimensions. So 52 is what the area was. We're increasing it by a scale factor of 2, but remember, that gets increased by 2, and that gets increased by 2. So together, it's actually being multiplied by 4. So it's 52 times 4, which would be, let's see, 52 times 2 is 104, 208 square centimeters. That's how much the area changes. So that's it. So take a look at it, at what I sent you, see if you have any questions. Everything I sent you is based upon what I talked about today. And as usual, I'm sure that there's some things I wasn't clear about, and you weren't here to ask me questions, so I really can't tell what you got and what you didn't get. But I will be totally available now. Please feel free to email me. I know that I haven't been available, and it's just been my fault, but everything is fixed, under control. We're ready to go. I have this one. I have one more I'm going to send you tomorrow, and then we will be done. I will send you everything I need you to turn back to me, and we have 3 weeks to get that into me. There's no time limit on it. Just make sure I get it back really by the 23rd or 24th, and then we're all good to go. So thank you for your patience, and I hope you have a great day.